Welcome dear learners, welcome in the second week of our MOOC on Industrial Pharmacy First. In the week 1, we have been in good learning environment with the concept of pre-formulation. We studied how the factors like crystallinity, like particle size, particle shape and other factors like flow properties, partition coefficient and polymorphism, how they affect the pre-formulation. We studied those factors. As far as the learning outcome is concerned, after completing this module, you will be able to understand the major chemical reaction and their effect in pre-formulation. In this particular module, we will be studying the hydrolysis, oxidation, reduction like major chemical reactions and how they are affecting the pre-formulation. Before beginning this module, I would like to begin with the open question for all of you. Dear learners, may I ask you a question? This question, the answer may come in any moment, in any time in the module. You will have to be attentive for that. So, please listen to the question. What are the redox reactions? What do you mean by redox? Okay, got my point? Now, with this open question, may I have the privilege to ask a question to Jenny. Jenny, do you remember the 3 key words which we were enchanting in the entire previous week? What were those 3 key words? Do you remember?
Yes, I remember.
Yes, yes, tell me.
Stable, effective and safe.
Got it. Good attempt, Jenny. So, dear learners, yes, stable, effective and safe. These are those 3 key words, and in this respective of these 3 key words, the pre-formulation and chemical reactions we will be discussing in this module. Now, pre-formulation, when we are discussing about the pre-formulation, first thing we should keep in mind that API is likely to undergo the changes due to many chemical reactions with the passage of time during storage, during processing, during the shelf life. So, the degradation through various chemical reaction is triggered by various factors like you know very well, temperature, pH, humidity and light. These are the factors which affect. Now, when we are saying that we are aiming the stability factor, that particular domain of the pre-formulation, the pre-formulation aims to ensure the stability of API during storage, processing and shelf life. Now, let us see the major chemical reactions one by one. First, hydrolysis. You know very well that it is the most common degradation reaction. Water, a universal solvent it is. So, the hydrolysis is almost always associated with any formulation development directly or indirectly. We cannot avoid the hydrolysis reaction. Now, how will you define the hydrolysis? For a drug in a solution, it is a nucleophilic attack of labile bonds by water. Or you can say like that hydrolysis is a 2-stage process in which a nucleophile such as water or hydroxyl ion adds to, for example, an acyl carbon to form an intermediate from which the leaving group breaks away in the second stage. Say for example, you see the structure RCX, RCOX. If you say that these X may be of 2 types, and depending upon that the hydrolysis reactions may be divided into 2 types, type 1 hydrolysis and type 2 hydrolysis. In the type 1 hydrolysis, the X may be ester or amide, while in the type 2 hydrolysis this may be a halogen or any other leaving group. So, type 1 hydrolysis reactions are catalyzed by acid or base and hence they can be well controlled by pH modulation. I suggest you to come with those example or acid or base catalyzed hydrolysis. Please dear learners, please get back to us in the discussion forum with some examples of these type of reactions, these type of hydrolysis. We will be waiting for you in the discussion forum with this thing. Now, as far as the example is concerned, for acid base reactions, the hydrolytic prone compounds are esters, example is aspirin, in thiol esters, spironolactone, amide, chloramphenicol, sulfonamide and others. Now, let me begin with the classic example of hydrolysis of atropine. Atropine undergoes hydrolysis at the pH greater than 4. Higher the pH, lower the stability, and that is why the soda lime glasses are avoided as container of this atropine. Why? Because soda lime glasses increases the pH with the passage of time because of leaching. So, aqueous atropine solution must be buffered at around pH 3.5 to 4 to ensure the stability. Now, taking another example of hydrolysis of procaine. Procaine is an anesthetic agent. It undergoes acid catalyzed hydrolysis below pH 2.5, while the base catalyzed hydrolysis and other reactions are there at greater than 5.5 pH, and there is a maximum stability at around pH 3.5. Hydrolysis protection is done by increasing the solubility in a non-aqueous solvent, and the second mode is by micellization of the drug using surfactant for shielding the drug hydrolysis. Now, we put that procaine into a micelle of the surfactant, and that is why this is protected from the hydrolysis. It is called shielding like thing. Okay. Now, moving to the factors affecting the hydrolysis, there are so many factors: solution pH, now buffer, ionic strength, use of non-aqueous solvents, presence of co-solvents, presence of complexing agent, surfactants and some other factors like temperature and humidity. Now, moving one by one, that pH, buffer, ionic strength, we have covered it in our previous modules. So, we will not be discussing it in detail at this moment. So, please refer some examples of this category. Now, moving to the solvents. For the intramuscular and subcutaneous routes, the use of non-aqueous vehicles may be considered as a method of avoiding hydrolysis. Same we studied in the procaine example. We studied the procaine example, the same holds true here. So, on the other hand, the use of a co-solvent, a water miscible solvent in the formulation may increase the stability by either suppressing the ionization or by reducing the extreme of pH required to achieve the solubility, or by reducing the water activity by reducing the polarity of the solvents. So, that is why we use the 20% of propylene glycol in chlorodiazoxide hydrochloride injection. Another factor: complexation, micellization, solubilization. It is a well practiced method of protecting the drugs. Now, we can complex the drug with some big ligands, various complexing agents like EDTA, lipids. They may shield the prone groups of the drug and hence protecting it from the hydrolysis. Micellization with surfactants and other molecules also shield the molecule from the hydrolytic attack. Solubilization, either you do it by co-solvent, by complexation or micellization. They show a modifying effect on the rate of hydrolysis of drugs. As far as the location part is concerned, you can see in this figure that the location of non-polar and polar compounds in the micelle govern their level of protection from hydrolysis. Non-polar compounds, you can see when they are in deep core of this micelle, they are protected better as compared to the polar compounds, because they are residing in the outer surface, in the micellar surface. That is why they are more protected. The non-polar compounds are better protected in the micelles. Dear learners, moving to the another blend of factor, temperature and humidity. The higher temperatures may reduce the moisture content of the product, thus slowing down the hydrolysis, while on the other hand the humidity may trigger the hydrolytic degradation. So, I again invite you for giving more and more example for this kind of factors. So, we have covered hydrolysis so far, and we learned what is hydrolysis. This is very common. How we can prevent the hydrolysis? By modifying the pH, or what are the other factors which can be modulated for hydrolysis. Now, we will move to the another important chemical reaction, oxidation. So, dear learners, we are here with the oxidation. Oxidation is the second most common chemical reaction after the hydrolysis. Oxygen, as you know, is a very common element present, and that is why the sensitivity to oxidation is almost common for many molecules. So, what is the oxidation? Removal of hydrogen atom, addition of oxygen atom to a carbon atom is called oxidation. Understand? Remember your +2 standard when you have learned this definition, the removal of hydrogen and addition of oxygen. I would like to quote, I would like to emphasize that I have given a web link, a YouTube channel link, that please go through that video, wonderful video. That presenter have very nicely described and tried to put it in your mind that what is oxidation, what is reduction. Okay. What is oxidation? It says loss of electron is oxidation, LEO. It is called LEO. LEO, oxidation. The most difficult reaction it is. It is difficult to prevent. It is accelerated by presence of trace metals, and it should be understood for the molecules under the study in the pre-formulation, and the formulation should contain suitable and compatible antioxidant or the blend of antioxidants to prevent the same. So, these oxidation reactions are prevented by use of antioxidants. These antioxidants are of generally of two types, type 1 antioxidants and type 2 antioxidants. Type 1 antioxidants are water soluble, while the type 2 antioxidants are oil soluble. In the water soluble, examples are sodium bisulfite, bisulfate, metabisulfite, thiosulfate, sodium formaldehyde, and etc. Please learn the examples. No, in the type 2 oil soluble, PG, propyl gallate, and BHA, butylated hydroxyanisole, BHT, butylated hydroxytoluene, and other examples. Learn this. So, the oxidation problem is very common with vitamins and iron supplements. When we are formulating these vitamins and minerals, it is a very common problem. In this case, a little amount as allowed by the regulatory agencies or the regulatory bodies like FIP is added extra into the formulation to achieve the desired shelf life. This is called overages. Now, let me define the overages. Verbatim definition you must learn, that is prescribed by the FIP, that which is International Pharmaceutical Federation. It defines overages as the voluntary introduction of, remember first thing, voluntary introduction. It is not accidental introduction, it is the voluntary introduction of a specific axis, second keyword, specific axis, during the manufacture of pharmaceutical forms of medicament that are unstable by nature and difficult to stabilize in order to maintain during their period of use an active content within the limits compatible with therapeutic requirements is called overages. Okay. So, keywords you must learn, then and only then you can learn the verbatim definition. Okay. So, as far as preventing the oxidation is concerned, always use suitable antioxidants. There are a list of antioxidants, you must learn what kind of antioxidant it is and in which percentage it is used in the formulations. Okay. And also see the effects of antioxidant. You cannot play with the antioxidant, you cannot choose any antioxidant for any formulation. What you have to see, what kind of formulation you are going to prepare, and most common antioxidant like that metabisulfite, it catalyzes the hydrolysis reaction. So, you will also have to see the effect of antioxidant on the other reactions. So, let me summarize the oxidation for you. Oxidation, LEO, loss of electron is oxidation, increase of oxidation number is also oxidation. Learn these definitions Okay. Now, this is very important to have the knowledge of antioxidants, and class 2, class 1, type 1 and type 2 antioxidants are there. So, after the oxidation we will move to the another domain of major chemical reaction, that is reduction. Talking about the reduction, let me discuss the reduction, which is one of the major chemical reaction. It is the third most important chemical reaction. It is indispensable with oxidation reaction. If one thing is oxidized, the other reactant is reduced. Reduction, same wavelength, removal of oxygen atom or addition of hydrogen atom to the carbon atom is called reduction. It is reversible with respect to the oxidation. In the reverse way, the definition holds true. There was LEO, loss of electron, is called oxidation. Here it is GER, gain of electron is reduction, GER. Remember this thing. Unlike oxidation, where oxidation number increases, here oxidation number decreases in case of reduction. An alkene upon reduction forms the corresponding alkane by reacting with hydrogen. So, all the factors which holds true or which affect the oxidation, they are same with the reduction. With respect to the reduction, the same factors will be applied. In case oxidation is being prevented, the same time we are preventing the reduction also. So, if A is losing an electron and B is gaining it, A is being oxidized and B is reduced. So, what is the problem here? It is the, let me give you the homework for you, dear learners. Can we have some classic examples of reduction? I will wait for your answers in discussion forum. Please do share the examples. Free softwares like ChemDoodle and XDrawChem are available for drawing structures, and even if you are not comfortable with that, don't do that. Just draw them by hand, scan them and put it onto the discussion forum. We will be waiting for your responses. Okay. I am hearing some voice. Jenny, Jenny.
I have an answer.
Yes, dear learners, Jenny wants to address our opening question. What was our opening question? What is called redox? See. So, redox. What is called redox? Yes, please give your answer.
Combination of reduction oxidation.
Okay, very good. It is just combination of reduction oxidation, because they are coupled together. Obviously, when we saw this thing, she got my answer with that animation, that electron is losing and in the same time the electron is being gained by another molecule. That is why if one is being reduced, second one is being oxidized. That is why it is called redox, and that is why it is called indispensable. So, here you got the answer, dear learners. After these major chemical reactions, let me tell you about the effect of temperature on the process of degradation. And as a general rule, process of degradation increases when the temperature increases. And by the standard thumb rule or standard rule, if you increase the reaction rate by 10 degrees Celsius, the chemical reaction increases by a factor of 2 to 3. The reaction rates are proportional to the number of collisions per unit time. Number of collisions of what? Atoms. Basically, the molecules are colliding with each other, Brownian motion, and the frequency of collisions increases with increase of temperature. Actually, in Brownian motion, these molecules are striking with each other. When you increase the temperature, that frequency increases. The Arrhenius described this concept, the dependency of temperature and these collisions and the chemical reaction. So, Arrhenius equations was studied and given by the Arrhenius. Arrhenius actually studied the effect of temperature on the reaction rate constant K and expressed their relationship by the following equation. this is which is called Arrhenius equation, that is K is equal to A e to the power minus E A upon R T, where A is a constant which is termed as the frequency factor, E A is the activation energy, R is a gas constant and T is a absolute temperature. So, if you take the log of this thing, this equation will be there, log K is equal to log A minus E A upon 2.303 R T, and if you integrate this equation between the limits of K1 and K2 and T1 and T2, the following equation will be obtained. So, log K2 upon K1 is equal to minus E2 into T2 minus T1 upon 2.303 R into T1 T2. If you plot this log of K with respect to the inverse of absolute temperature, means 1 by T, you will get a slope. That slope will be minus E upon 2.303 R. By this way, we can have a concept, or we can have a trend of change of reaction rate with respect to the time. However, Arrhenius equation has got some limitations which we will not be discussing here, but you must study what are the limitations of Arrhenius equation. Actually, it is not holds each and every time with practical aspects or with practical scenarios everywhere, but in general terms it holds almost true. Now, moving to the another factor, relative humidity. Now, Jenny, have you been in some coastal areas?
Yes, I visited one coastal area.
May I ask where I have been?
Goa.
Okay, did you enjoy there?
Yes, I enjoyed a lot.
That's good, that's good, that's good. So, actually, what did you observe there? Can you feel that stickiness onto your skins in that environment, in that climatic condition? This is called humidity, you know. These people know what is the humidity actually. And another question from Jenny. Jenny, may I ask the question that in which particular season your things like biscuits, snacks and sugar, when kept in open, get sticky, get the moisture?
In rainy season.
Yes, simply it is the rainy season. So, dear learners, what is special in rainy season? Actually, the moisture present in the air, the water vapor is present there in the environment, that is called humidity. Water vapor carrying capacity of air is called humidity. The water vapor present in the air should be controlled in the pharma plant also, and the storage condition, the vapor present in that air, the moisture, when it is absorbed onto the drug or the excipients, it may trigger the degradation reactions of hydrolytic reduction, oxidation reduction and other kind of reduction, including the microbial degradation. These adsorbed films of moisture are saturated with drugs compared to the dilute solutions as in injectables. So, when a piece of air of certain temperature and pressure is saturated with the water vapors, then the humidity of that air is called saturation humidity, and we call it 100% RH. And depending upon that, we state that the this environment is this percent RH, this environment is this percent RH. So, we calculate that percentage from that saturation humidity. Okay. So, at a particular temperature and pressure, air can carry maximum a particular amount of moisture. After that, it condensed. You might have experienced that thing, you know, in the summers. If you pour chilled water into a polished steel glass or in a glass, but you observe the dew formation on the outer surface of that container. This is because this happens. Why? Because it has caused that dew points have been achieved, because the air was unable to carry that moisture at that temperature. So, it is the effect of humidity. Now, relative humidity is basically the difference of partial vapor pressure of the surface and the free vapor pressure of the environment. This is the driving force there. Now, higher the relative humidity, higher will be the water absorption onto the drugs or the excipients. So, any other associated degradation reaction may occur at that higher relative humidity. So, the drug in crystal form may be damp if exposed to higher relative humidity environment. So, to ensure the stability, a critical humidity must be maintained so as to make the drug or excipient dry. No, why you keep your snacks, biscuits and other things into your refrigerator when they are opened? You might have experienced that, because that condition, that humidity is controlled there in your refrigerator. Okay. So, ICH guidelines in the same way on stability gives the specific range of relative humidity along with temperature for performing the stability studies. Now, the last factor is photolysis. The various drugs are sensitive to the sunlight, and upon exposure to the light, these are degraded. For example, the most common example include indomethacin, amphotericin B, riboflavin, tetracycline. Can you come with some other examples, dear learners? I will wait. Please do remember, if you will put a little effort, you will learn more. The energy associated with the light radiation increases from UV light to the IR, but it is independent of temperature. Out of that entire EMR range, electromagnetic radiation from 280 to 790 nanometer, the UV range, which is 280 to 320 nanometer, is the one which causes the photodegradation. The photons are absorbed, these light photons are absorbed at a particular wavelength by molecules, and then depending on the nature of drug, it may cause either degradation or energy or heat emission or emission of light at new wavelength, phosphorescence or fluorescence it may be. So, you can avoid the photolysis by proper packaging, by working in dark environment, covering the apparatus by dark paper, film, using amber glass bottles, cardboard outers, aluminum foil overwraps and blisters. So, we have come to the end of this module. Let me summarize the things for you, that we studied the major chemical reactions, hydrolysis, oxidation, reductions, which are the major chemical reactions. These are the degradation pathway. In pre-formulation, the sensitivity of the drug and the excipients must be studied, and the protection of drug and excipients against these reactions must be ensured using antioxidant and other aspects which we have discussed. Effect of temperature, relative humidity, photolysis should also be studied for each and every molecule. If some drug is photosensitive, then you must take the suitable precautions. So, as usual, finally, I suggest you to refer the further readings. I have especially emphasized on one particular URL. Please go through that and learn the things in very effective manner again, and do take part in the discussion forum. I have given the homework for you. I will wait for you guys. So, bye for now, and if you have any query, we are here to solve your problems in the discussion forum. Happy learning, guys.